I'd like to thank the organizers first for inviting me to give a talk at this conference, dedicated to Professor Srinivasan's on his 70th birthday. I first met him many years ago when I had applied to a conference at KITP, and then I forgot about it. And he happened to be organizing it. So when a few months later when he came, he made it a point to call me and inform me that he was one of the organizers and the reason why I couldn't be accommodated at that particular time. And he encouraged me to apply for future conference. And that is something he's been doing for all of us working in India for many years now. Taking a keen interest in how we are progressing and intervening at key moments to help us along. And for that, I'd like to thank him for that. I'm sure many of us would like to. And I wish him many more years of progress in science as well as many more years of happiness. So I've called this soft wall turbulence. What I will try to do, since this is the last talk of this conference, I'll try to make it mostly experimental, show you some experimental results and try to sort of indicate what is it that we understand and the things that we don't understand. And you can sort of tell me whether we do actually understand what we think we do. And it'll give some food for thought for things that we don't understand. These are the various people who have worked on this over the years. And the experiments were mostly done by Mohan Verma and Sagar Srinivas at ISC. And I'd like to acknowledge EST and the JRD Tata Trust. 2 slides of introduction. This talk is going to be in the asymptotic limit of low Reynolds number. Okay, so can you have turbulence in the asymptotic limit of low Reynolds number? There's a sort of counterpoint to everything that has gone on before. And also it'll be purely experimental. So in that sense also a counterpoint. So in a rigid tube, the transition from laminar to turbulent flow was first observed by Reynolds in the late 19th century. And this is evidence, these pictures have been shown before, that if you inject a dye stream at the center of a tube, then at low velocities, it's a nice straight line. At some point, there's a discontinuous breakup, and then you go to a turbulent flow. The point at which it breaks up is roughly 2100 for a pipe flow, and about 1200 Reynolds number for a tube. And at that point, also, you see a discontinuous change in the friction factor, which is a scaled pressure difference required to drive the flow. And it's important that this is discontinuous. Because if you do linear analysis, you'll find that the system is always stable for a pipe flow. For channels, there are theorems which tell you that the flow cannot be unstable if you neglect viscosity. And so an inviscid profile is always stable. If you do include viscous effects, the flow does become unstable, but because of viscous internal layers of thickness, Re power minus 1/3 in the flow. This 5700 is still much larger than the transition Reynolds number of 1200 that is observed in experiments. And that is supposed to be because it is a highly subcritical transition. So this is still, the transition in the flow through rigid tubes and channels is still not a satisfactorily solved problem even today. And there have been some new ideas over the years, and but it's fair to say that it is still not completely solved. What about the turbulence characteristics? So I'll talk about a little bit about turbulence in a rigid channel, and this gives me a way to introduce the kind of experiments that we do. So these are typically done in a rectangular bore within a block, which is made usually of acrylamide gel, but it could be made of other gels. And you can see the dimensions here. The bore itself has dimensions of about a centimeter times about 0.6 to 1.8 millimeters. Okay, so the height is the smallest dimension here. It's between 0.6 and 1.8 millimeters. And the block itself, it has a height of about 1.5 centimeters, a width of about 1.5 centimeters, and a length, in this case, that is about 25 centimeters. So we introduce a fluid here through a pressure gauge and a needle valve. And we can actually look through the side. So polyacrylamide gel contains almost 90% water, so the refractive indices are approximately equal. So if you do seed the flow within, and you shine a laser from the top here along the center line, you can look from the side and you can image it. Okay? These experiments need to be done carefully. First of all, you've got to make sure that the bore is perfectly flat. And since the height is only about half a millimeter, the particles that you're using for seeding the flow have to be very small. So we typically use about 10 to 15 micron particles. And the problem with that is that you cannot get measurements within about 30 microns from the wall because the particle size itself is about 10 to 15 microns. Okay, so this shows the larger setup. We shine laser from the top, look from the side, and determine the velocity profiles, fluctuating velocities along the center line, okay, in the span-wise direction. In everything that I will say, X is the flow direction, Y is the cross-stream direction measured from one of the walls, okay, and Z is the span-wise direction. Okay? And you can take images at different locations. Okay? So if you do this in a rigid channel, which is sufficiently rigid, you recover the velocity profiles and so on for turbulence. In this case, I've done the validation to the Reynolds number of about 3,500. And the bottom and left axis are actual dimensions of the channel. The right and the top are scaled by the friction scales. And you can see that the points are the experiments and the lines are results from DNS simulations. And they agree quite well. The agreement is not as satisfactory near the walls. Okay? That is because a small change in the X direction will result in a relatively large change in the velocity. Okay? At this Reynolds number of 3,500, we do recover the viscous sublayer and the logarithmic layer. Not too well, but we see some signature of that. Okay? If you plot it on a one common plot. Okay? We have only about a couple of points in the viscous sublayer, and that is one of the limitations, as I said earlier. Okay? So the logarithmic layer, also the slope is slightly wrong. This is supposed to extend between about 5 and about 20. Okay? And then the inertial sublayer is between about 30 and about 200. Because of the low dimensions, we do not go all the way to 200 in our scales. We also recover the fluctuating velocities, the RMS of the fluctuating velocities across the channel in this configuration. So this is the streamwise fluctuating velocity. This is the cross-stream fluctuating velocity. You can see there are large error bars, but subject to that, they are in agreement with the results from direct numerical simulations for this particular configuration. I should note that the streamwise fluctuating velocities have a large peak close to the wall, which is due to the bursting of eddies, which generates turbulent flows. Source of the big error bars is because we are averaging over 8,000 frames in units of 500 frames each, and over 15 seconds. And there is slight variations in the conditions from one experiment to the other, because we are controlling it with a needle valve and we measure the velocity profile only after the fact. Okay, so what should change if the walls were made soft? Okay, previously we had only the fluid properties and the length scale, so you could only scale the velocity one way, and that was the Reynolds number. Okay, now if the wall material were elastic, you have another parameter here. Okay. And you can get a dimensionless number, which is a function of the wall elasticity and the fluid viscosity. Okay? And it is independent of the Reynolds number, so independent of the flow velocity. So it is only a property of the configuration and the materials. Okay? So you would expect just from dimensional analysis that these two have to be related. The transition Reynolds number may in some way be related to this additional parameter. And we are talking about very soft interfaces. They are about 10 power minus 6 times the elasticity modulus of steel or glass, things like that. So I'll just tell you what the experiments were. I'll talk a little bit about what the theoretical predictions tell us and some open questions, and I won't go into mixing. So this is how we modify our channel now. So we make this section here of soft gel. The section over here is still of hard gel. And this section is required so that the flow disturbances introduced at the inlet are damped out before it reaches the soft section. Okay? So once again, we have about 13 centimeters of development section, about 14 centimeters of test section. Channel height is 0.6 and 1.8 millimeters. Width is about 1.3 centimeters again. And we flow through and we make measurements at different downstream locations. This is a top view. And I should mention here that when we do apply a pressure gradient, there is a channel deformation if the section is soft. This channel deformation is approximately 1% for the largest pressures that we use. Okay? So the slope is about 1%, even though the channel deforms by about half a millimeter or so. Okay? And these are the configurations. So we can look from the side, get PIV measurements. We also have a way of looking from the top and looking at the top and the bottom surface of this channel. We can put little beads into the top and bottom surfaces and look for the displacements. So we can do two kinds of displacement measurements. One is to put a bead on the walls and see if the wall is moving upwards and downwards, okay, in the vertical direction by shining light from the top. We can also put beads within the wall and look from above and see if they move horizontally, okay, on the wall of the channel. So channel height, I said, was 0.6 to 1.8 millimeters. Elasticity modulus is 0.75 kilopascals and 2.19 kilopascals for the configurations that we've used. The dimensionless parameters, here I will define the Reynolds number based upon the flow rate and the channel width. Okay? So that way it becomes independent of the height, because height deforms in our experiments. And the measurements that we do are the fluctuating velocities, the cross correlation, the mean velocity, the wall displacements perpendicular to the surface, as well as we can look from the top and do wall displacements parallel to the surface. So mean velocity profiles first, and I've shown it for different Reynolds numbers, 278, 301, 335, 545, and so on. The first thing you can see is that for the black Reynolds numbers, I've also plotted in the dashed lines the parabolic velocity profile. Okay, so the black Reynolds numbers, the actual velocity profile coincides with the parabolic velocity profile. When you come to the blue, you see that there's a significant difference between the parabolic profile and the actual velocity profile in the channel. Okay? However, for the blue, the velocity profile is still symmetric. And when you increase the Reynolds number still higher, it becomes asymmetric. Let me just make one distinction which I forgot earlier. Okay? That is that all of these are done with the bottom surface fixed and the top surface free. Okay? I could also do experiments where both surfaces were fixed. Okay? So that would be a symmetric configuration. Whereas if the bottom surface is fixed and the top surface is free, that's an asymmetric configuration. Okay? And the transition to this asymmetric, possible deflection of the top free surface, And these asymmetric profiles are seen only when the top surface is free, in which case you have an asymmetric deflection, as I will show you. Okay? Now, where the mean velocity transitions from the parabolic velocity profile, you see an increase in the root mean square streamwise velocity fluctuations, but they are still symmetric. They seem to form the kinds of peaks that you would see in normal turbulent flows. And when it becomes asymmetric, the fluctuations also become asymmetric. Okay? So near the top surface, the fluctuations end up becoming asymmetric. And those are the red profiles. And along with this, you also see sharp increases in the velocity fluctuations in the cross-stream direction, okay, and in the Reynolds stress, okay, Reynolds stress per unit volume. Okay. I was careful in the beginning to say that we cannot get measurements within about 30 microns of the wall, and those are these regions here, okay? And so I have not plotted those. Now, from the experiments that we can see, it looks like the velocity profile, fluctuating velocities may be non-zero at the wall itself, okay? But we cannot say that from the extrapolations that are observed here, okay? But it is sort of difficult to extrapolate the Reynolds stress in such a way that you go to zero, okay? So that is a question that is still not answered. Are the velocity fluctuations zero or non-zero at the wall itself? We do not have the resolution for that. But one thing that we can do is to actually look at the shear stress profiles, okay? So in this particular case, I show the total stress, that is the Reynolds stress plus the viscous stress. And in the dashed lines, I show only the viscous stress, which is obtained from the derivative of the mean velocity, okay? And these things seem to be different at the wall, okay? It is very difficult for us to get something close to a linear stress profile as you would expect for a channel flow with a constant pressure gradient if you do not include a non-zero Reynolds stress at the wall, okay? So this seems to indicate that there are non-trivial velocity fluctuations at the wall, and the fluctuating velocities do not go to zero. Okay? On a von Neumann plot, okay, so the black, the viscous sublayer solution fits close to the wall, and these are parabolic profiles. Okay? When you go to the blue symmetric fluctuations, you can see that a logarithmic law fits very well close to the wall. Okay? The constants in the log law are different from the von Neumann constants. Okay? But however, when you go from the blue to the red, there is once again a shift, okay? And the logarithmic law no longer seems to fit. Now you can make various measurements to tell you whether you're in the laminar or the turbulent flow, or the after transition, by looking at the difference between the actual velocity and the laminar parabolic velocity, a measure of that, the maximum of the fluctuations across the channel. And you can plot all of these, and in each of these measures, you will see a transition, okay? So you can see that for the difference between the velocity and the parabolic velocity profile, it is close to zero, and at about 300 or so, you see a shift, okay? And then there's a second shift here, okay? Indicating two distinct transitions, okay? I've shown it for two different shear modulus here. The point at which transition takes place is different. It's higher as you go to a higher shear modulus, but you see two distinct shifts. You see it in the streamwise velocity as well. Okay, you see one shift here, and there's a second shift here, okay, indicating two distinct transitions. The magnitude of the fluctuating velocities after the first transition are much higher than the increase in the magnitude that you would have for the hard wall laminar to turbulent transition, okay? Many times higher. Okay? So the intensities are much higher. And the same thing holds for the cross-stream fluctuating velocities and the Reynolds stress. These are the wall displacement measurements that we have made, okay? So on the left axis is the horizontal displacement measurements. On the right axis, reference to an inverted scale, is the vertical measurements. Okay? So let's take the horizontal first. After the first transition, you see there is generation of horizontal displacement fluctuations in the wall, okay? And then after the second transition, these horizontal fluctuations once again increase, but only on the top wall, okay? There's virtually no increase in the bottom wall. Okay? If you look at the vertical fluctuations, the zero is here, okay? It's an inverted scale. At the point where you start to see horizontal fluctuations in both walls, you see that there is virtually no vertical fluctuations. At the second transition, where you see the increase only at the top wall, you see vertical fluctuations as well. Okay, so this indicates that after the first transition, the wall motion is primarily horizontal. And then there's a second transition, then you have vertical fluctuations, but that is only on the top unrestrained wall. And the same thing holds for the others, for the gel with the higher shear modulus as well. The frequency spectra of the fluctuations after the blue transition, okay, which I will call the soft wall transition, you do not see any sharp structure, but after the second transition, okay, which I call the wall flutter transition, you see a sharp peak. Okay. The frequency correlates very well with the frequency you would get just from the speed of shear waves in the material and the height of the channel. Okay. Now, so all this was done for a channel with height 0.6 millimeters. Okay. Now, so this seems to indicate that the transition takes place only from a laminar flow, because the transition Reynolds numbers in this case are all less than 1200. Okay. However, if you go to a higher channel height, you find that the transition takes place even if the flow before transition was turbulent. Okay, so let me walk you through that. 768 is a laminar flow. Okay. 1071 and 1332 are turbulent flows after the turbulent hard wall laminar to turbulent transition. And you can see there's a shift in the velocity profile from the laminar flow. Okay. After that, you get another transition to these blue curves, okay, which are at 1515 and 1734, which are now symmetric, but they involve wall oscillation. And then you get an asymmetric profile at 1973. Okay. So this transition from the hard wall turbulence to the soft wall turbulence happens even if the system is already in a turbulent state. Okay. And the same thing that you see in the mean square fluctuations. And you can see it's not clear here. There is one transition here. This is the hard wall. HW is the hard wall laminar to turbulent transition. Okay? And then the difference in the velocity is approximately a constant until you get on the second transition, okay, which is due to the soft wall transition with horizontal fluctuations, and then a third transition. Okay? And that is reflected in the mean square velocities the streamwise as well as the cross-stream direction. The error bars are large here, but you can sort of see that there are distinct transitions in this case as well. And the same thing is reflected in the wall displacement. Okay, so once again, the left axis is the horizontal displacement. Right axis, inverted scale, is the vertical displacement. Okay, at the hard wall laminar turbulent transition, there is virtually no displacement fluctuations on either wall. Okay, after that, there is a second transition where these horizontal fluctuations start to take off. Okay, that is the soft wall transition. At that point, you see virtually no vertical fluctuations. Okay, and then there's a second Reynolds number at which you get this vertical motion as well. Okay, and at that point, you see a large increase in the vertical displacement fluctuations. So I tried to show you that there are two distinct transitions that take place even after the laminar to turbulent transition. Okay, the soft wall transition, which basically involves tangential motion of the wall and no visible normal motion. Okay, the characteristic peak in the streamwise fluctuating velocity close to the wall, and the fluctuating profiles are symmetric. Okay, there is no visible viscous sublayer that we can see down to the resolutions. There is a logarithmic layer, but the log law, the constants depend upon the wall elasticity. Okay, and there's a question of whether there's a characteristic frequency or not. And then there's a second one, which I call the wall flutter transition. It happens only if the top wall is unrestrained. There's a normal wall velocity only at the top wall. Okay, the wall displacement profiles are asymmetric, and once again, there is no viscous sublayer, but the characteristic frequency is the same as the shear wave speed in the solid. Okay. So how do you explain this? So in the case of flow past viscoelastic medium, there are, in addition to the fluid velocity field, the displacement field in the wall is a dynamical parameter. Okay? And that has to be described by an elasticity equation. Okay? The elasticity equation can be done, you can write a linear elasticity equation, but still the strain measure is typically nonlinear. Okay? So you have to include that. And the dimensional parameters I'd already discussed, and from that you get two dimensionless parameters. So what you have to do is, in the stability analysis, you have to actually consider cases where the surface is deformed, and therefore the velocity at the surface, at the deformed surface, you have to apply the continuity of velocity and continuity of stress conditions. And these conditions are of this form, where this is a substantial derivative of the displacement field. Okay? It turns out that there are multiple modes of instability. Okay? There are modifications of the rigid wall instabilities, but there are other instabilities that are qualitatively different from what you get in the flow past rigid surface. Okay. In the limit of high Reynolds number, see, one regime that you can straight away consider is where the elasticity modulus goes as rho v square. Okay. So there's a balance between the inertial and the forces in the fluid and the elastic forces in the solid. And that translates to Re goes as sigma to the half. And in this case, the Rayleigh theorem and so on don't apply because the velocity is non-zero at the surface, whereas the Rayleigh theorem assumes the velocity has to be zero. Okay? There are still internal critical layers. Okay? You can solve the Orr-Sommerfeld equation and couple it to the equation of the displacement field. And you will find that there are critical layers within the fluid where viscosity is still important. And based upon this, you get multiple solutions, unstable solutions in this Re sigma space, but they do not extend all the way to the limit of zero Reynolds number. Okay. If you consider the limit of zero Reynolds number, then you could have a balance between the elastic stresses and the viscous stresses when this parameter is order 1, or Re proportional to sigma. The equations themselves are linear. There is no coupling between the mean flow and the fluctuations. However, there's a coupling that enters through the tangential velocity condition. So if you had a shear flow past an elastic surface that is stationary, if the surface is displaced, the fluid velocity at the displaced surface, okay, consists of a part due to the strain rate times the displacement itself. Okay? And because of that, you get a coupling through the tangential velocity boundary conditions. And this could act as a mode for the transfer of energy from the mean flow to the fluctuations due to the shear work done at the interface. Okay? And it's necessary to include tangential displacement of the interface in order for inducing this instability. Okay? And this has also been well studied. This is a finite wave number instability. And we can get the critical Reynolds number as a function of wave number and so on. Now, in the high Reynolds number limit, there is also another instability which is called the wall layer instability. Okay? So this actually exists even in the flow past a rigid surface, but this mode is always stable. Okay? So quite simply, if you take a linear velocity profile close to the surface, and you scale the vorticity equation, for example, the convective term is proportional to y, and the diffusive term has 1 over y squared. So you can have a balance when the Re power minus 1/3 times y is order 1. Okay? So the boundary layer thickness versus Re power minus 1/3. Okay? And if you rescale the equations and solve them, you will find that there's an instability in which the transition Reynolds number is proportional to sigma to the 3/4 power. Okay? And these are the asymptotic lines, and these are the numerical lines for one particular realization of this geometry. So you have multiple modes of instability. Okay, there is a viscous, there's the inertial instability here. There's a low Reynolds number instability which continues onto the lowest of the wall mode instabilities, and there are multiple solutions for the wall mode instabilities. And this is actually subcritical, okay, the viscous instability, whereas the wall mode instability is supercritical. And the mechanisms are different. So for the high Reynolds number instability, where R is proportional to sigma to the half, the Reynolds stress due to an internal viscous layer is what destabilizes the system. Whereas for the wall mode, it is a wall viscous layer of thickness Re to the minus 1/3. And the mechanism is the shear work done at the interface. And the same for the viscous instability. Okay, so what do these all have to do with the transition itself? Okay, so the experiments that I just told you, the soft wall transition, okay, appears to follow the same scaling as the wall mode instability. Okay, so what I've put here is experiments over many decades in this parameter sigma, showing the transition Reynolds number versus this parameter sigma. Okay, and these lowest experiments were actually done in microchannels of height about 35 microns. Okay, and these were done in channels of about 2 millimeters in height. Okay, and they follow the scaling law, sigma to the 5/8, reasonably well. Okay, there are deviations here because the wall deformation is actually very large in that case. But apart from that, there is fairly good scaling from multiple experiments done in multiple pieces of equipment. Okay? In order to get this transition Reynolds number correct, it is essential to be able to take into account the channel deformation. Okay? And due to the channel deformation, the velocity profile will change, the pressure gradient will change. Okay? And if you include all of these correctly, then the linear stability analysis quantitatively predicts the point at which transition takes place. And this is a counterpoint to the rigid wall transition, which is still not understood as of today. Okay? And the scaling is also applicable. If you take wall deformation into account, the 3/4 power changes to 5/8, but other than that, everything is fine. Okay? The wall flutter actually corresponds to an inviscid instability. Okay? And once again, you can get that quantitatively. The transition Reynolds number was a sigma to the half power, and that is these points here, okay, for the wall flutter instability that were taken from the work on the channel. The instability from a turbulent flow can also be understood as a wall mode instability, okay? Because if you had a flow that is already turbulent, there is a viscous sublayer within which the flow is still laminar, okay? And so long as that viscous sublayer thickness is much larger than the thickness of the critical layer in the wall mode analysis, the regular analysis should still apply, okay? So the viscous sublayer thickness, according to the old classical definition, is about 30 h by Re star, where Re star is the friction Reynolds number. Of course, recent work has, of course, modified that, but still, at such low Reynolds number, I can go by the classical estimate. The wall layer stability analysis, the wall layer thickness by h goes as Re power minus 1/3. So the stability analysis should be applicable if this condition is satisfied. Okay? And for our experiments, I've plotted this condition as a function of Reynolds number, and you can see that at the place where the transition takes place, it's actually quite small. Okay? So in that sense, it seems like the transitions can be quite well predicted by the standard stability analysis. Okay? But there are open questions. Okay? One is that there are very large turbulent fluctuations. Okay? So I shown the same graph that I showed you earlier. Okay? So look at, for example, Vx prime, the streamwise fluctuating velocity scaled by the flow average mean velocity. Okay? You see that at this point, there's a sharp increase. Okay? This increase is actually much larger than the increase that you have for the hard wall laminar turbulent flow. Okay? In fact, this increase is the kind of increase that you would get if you had a hard wall turbulence at a Reynolds number that is something like 20,000. Okay? Whereas this, we are getting at a Reynolds number of about 500 or so. Okay? And the same thing holds also. The cross-stream velocity fluctuations, you can see that it's about roughly about 5 times what you would get in a hard wall turbulence. And similarly for the Reynolds stress actually, okay, it's pretty large. Okay? So that is one open question. Ultra-fast mixing. So I didn't have a chance to go through that here, but mixing rates in these flows. Sorry? Yeah, why is the fluctuation so large? Yeah. I mean, if you use standard K epsilon models, you won't get such large fluctuations. Okay. Ultra-fast mixing is one. Velocity fluctuations at the wall. Okay, do they exist? Do they not exist? Do they decrease? So I should note that in these flows, if you calculate the Kolmogorov scale the usual way, it turns out to be about 3.5 microns, whereas the particles that we're using are about 15 microns. Okay, so that is still unresolved. Viscous sublayer and logarithmic layer. Okay. We see a clear logarithmic layer only for the intermediate regime where you have soft wall turbulence. We do not see it at lower laminar flows or hard wall turbulent flows at these Reynolds numbers, or at higher velocities after you go to some other, to the wall flutter turbulence. Okay? And wall frequency in dynamics is still an open question. Okay? And the other thing is really that, I mean, as a class of turbulent flows, okay, how much of this can be attributed to the wall fluctuations, and as opposed to what you would have the usual production within the flow, because from these graphs, if you plot the energy production rate, okay, in hard wall turbulence, it has a peak close to the wall and then it goes back to zero because the fluctuations have to go to zero. In these cases, if you just take simple-mindedly the actual fluctuation profiles you get, you will find that the maximum is actually at the wall, okay, not within the flow. So how to model those kinds of turbulent fluctuating production mechanisms. So those are several of the open questions. Okay. So that I'd like to thank you. I hope it has been reasonably light for the last talk of the session. I'd be happy to take any questions.
Questions? Questions?
The deformation at the wall, how do you take, because that is should be unsteady, right?
Yeah.
So how do you take that unsteadiness into account in your stability analysis as such?
We do not. We assume that the wall is stationary and then see at what point that flow configuration becomes unstable, and then calculate what is the frequency of the instability and try to see if it agrees. So the frequency for the second transition agrees very well, because you just take the shear wave velocity and divide it by the thickness square, you get a frequency, and that is in the same magnitude. The other one, actually, the frequency is of the order of 10 power 4 hertz, okay, about 10 kilohertz. And using imaging techniques, we don't have ways to measure it.
There's no question of any resonance.
The second instability could be due to a resonant coupling. The first one is not. No. Frequencies are higher, and also the penetration of the displacement fields into the wall is not all the way to the bottom.
Yeah, so the blood flow is something similar? No.
In all different talk, yeah. Yes, it is similar.
It is connected or no?
It is connected, yes. Of course, subject to caveats, it is oscillatory, it is, the walls are curved, and therefore you have a Dean flow in addition, and blood is not a Newtonian fluid, and so on. Okay, so there are many caveats there, but the transition to turbulence is still applicable.
You showed results from some simulations also.
Yeah.
Those were conducted with rigid walls and linear stability analysis, which accounted for elasticity of the wall. Do you see a way forward in combining them and doing nonlinear simulations of the real system?
Yeah. See, it's very difficult to put a wall in DNS because of the spectral procedure used in the cross-stream direction. That requires a flat surface. Okay. So in that case, the kind of DNSS that is done today is going to be difficult, unless you were to map it onto a rectangular domain and then use metric tensors. Okay. That has been done, but it has not given any useful results so far. The way forward that I really see is by mesoscale methods, if at all. Okay, if mesoscale methods become computationally competitive, then there is no need to. I mean, they apply for all complex geometries, everything, without any implications. So then we can, for example, model the elasticity also by mesoscale methods and then couple them easily. Okay. Otherwise, if you try to do finite difference for the wall and then DNS for the fluid and so on, it's going to be very complicated. And the other thing is at the time scales. So I said that the instability is of the order of 10 power 4 hertz. So you have to have, if you really want to solve it completely, you have to resolve much lower times than that.
About the connection, does it deform at the point of connection?
Yeah, yeah, it does deform at the point of connection. So the way you do it is that these are polymer gels. So you mix the monomer, the catalyst, and so on, and you pour it in, and then it'll gel by itself. So what we do is initially we mix a higher catalyst concentration to make it harder, pour it in for half the channel, okay, and then let it set, and then mix the lower concentration, then pour it in for the other half. Okay. They are connected seamlessly. There is probably deformation there, but I don't think that is dynamically significant, okay, because most of the processes that happen are far downstream. Okay. The wall deformation does matter, but when we calculate our laminar flows, we actually calculate them for the deformed geometry. When you do the stability analysis.
So, sorry. So, for the case of soft wall transition in turbulent flow, do you assume that the viscous layer or the inner layer up to 30 wall units is laminar? Because the production peaks at about y plus of 15. So even within the buffer layer,
yeah. So I mean,
you still have vigorous.
Okay, so you can decide. Okay, so it's at the point where transition takes place, it is about 10. Okay, yeah. Okay, roughly. So you can decide if it's applicable or not.
Do you measure fluctuations up to 30 before the soft wall transition?
No, I mean the measurements were all shown here. I mean. Yeah, these are the measurements. So the brown ones are after the hard wall transition. The brown ones here are after hard wall transition. Those are the fluctuations.
I'll talk to you.
Have you seen any manifestation, Kumaran? Yeah. Have you seen any manifestation of the viscous mode in the experiments?
Yeah, that's a different experiment, but yes.
So I mean, what do you have?
It agrees quantitatively. Yeah.
Just at very low RE, you see that first. And does it lead to turbulence or just a dynamic ordered state?
So it's a subcritical transition. So you need to use a very viscous fluid to reach that domain. So what we do typically is have a gel and then have a fluid like silicone oil with very high viscosity. And there, once the surface goes unstable, it sort of breaks up and little bits start to come off. So it's very difficult to hold it in a steady state. Because it's highly subcritical. Yeah. But the transition parameter agrees well with. That's been done many times. So. If we have fixed on both sides, we would have seen the first transition, but not the second transition.
Could you do the viscous mode simulations with something like a boundary integral method, which is like for Stokes?
Yeah, yes.
That might be one possible thing to do.
You can do that. Yeah, so the only point there is that the time dependence comes in because of the elasticity equation. So that ends up not being a Laplace equation, it ends up being a Poisson equation. So that's the only difference.